All right, with this video, I'm just gonna quickly go over some intro material on X-ray diffraction. So these slides are from MSE408-F20, so this is just meant to be a review and get us back into the field of X-ray diffraction. Okay, so X-rays, we use them because they have similar wavelengths to the spacing within crystals, so the interplanar spacings. So we're talking about on the order of 1 angstrom, and so this is going to be a common unit for us when we deal with X-ray diffraction. And we use it to determine the crystal structure. So this lab is going to be all about determining crystal structure and other information we can get from diffraction. All right, so this is also something we'll do in MSE408-F20, but we can also define sort of our characteristic equation in diffraction with Bragg's law. And this is a simple illustration of what we're looking at in Bragg's law. We're looking at adjacent planes, so A, B, C, and so forth, and we're looking at an incident beam that's in phase and what happens to it as it's diffracted, and how it has to sort of maintain that in phase. So basically we look at a beam 1 and beam 2, but obviously there's more than that. This is just a simple illustration. And so beam 2, which travels further into the material before it diffracts, so it goes to the second plane, travels an extra distance SQT, and so that SQT distance must be an integer value of the wavelength if it's going to maintain in phase. And so that's really the whole Bragg's law. And so when we do that, we get specific angles at which these waves stay in phase. And so this is the integer value of the wavelength, and then it's related to the interplanar spacing for the given plane, so DHKL, and then the sign of the angle that we use in this experiment, so theta. And then in all of our cases, we tend to use that the value for n is 1, and this means that we have first order reflections. So unless otherwise noted, you're just going to use n equal 1. All right, so in this lab, you will be using or indirectly using an X-ray diffractometer. And so this is a typical setup. It's kind of an old image, but it still works quite nicely. But this shows kind of all the moving parts of your diffractometer. So the target is your specimen that we're going to prepare. The copper target, this is part of the tube design that creates X-rays. So this is kind of showing the inner workings of the tube. So we get X-rays out of this. They're shot at the target with angle theta, and then we have a detector that detects the diffracted X-rays at the same angle theta. I wanted to show you this because this also kind of shows you about some of the other geometry. So if you're familiar with X-ray diffraction and the data that you get, you're probably familiar with the fact that all of the x-axes are in terms of 2 theta, not theta. And that is, strictly speaking, because of the geometry of the diffractometer. Because to make this all happen, the typical way for this to occur, and I believe I've got it here, so if we've got electrons that produce X-rays from targeting the copper, and then a filter filters out so that we only get the one wavelength, copper K alpha in this case. And then our incident X-rays interact with the specimen, and they are detected at the detector, and then the counts are counted as intensity, not on the chart recorder, but on the computer. So the way this occurs, and we scan to different angles so that we can detect a spectrum for different DHKL values. And so the way this works and the way why we have this 2 theta is because the target and the X-ray tube don't move, but the sample, the specimen target here, and the detector do move. So we move it in such a way where the specimen moves in increments of theta, but to maintain the Bragg geometry where we have the incident and diffracted beams both at theta, that means the detector has to move by 2 theta. So our specimen moves by theta, the detector moves by 2 theta, and that's why the measurements are going to be in terms of 2 theta, because that's what the machine is measuring. And so you just always have to keep that in mind about these x-axes being in terms of 2 theta. Okay, so I'll kind of skip through this, but this kind of talks a little bit about how the x-rays are produced by characteristic x-rays interacting with copper target. And then this is your data. This is kind of how it's reported. So again, Bragg, the diffraction angle 2 theta versus intensity. So we get a spectrum, and anywhere you see this peak means that there's been constructive interference, and that is one of those Bragg angles. So these are the important peaks. And so basically in this whole analysis, we're going to look at what these peaks represent. And from this graph, you can see that they've already identified them as being tied to particular sets of planes. And again, like I just mentioned, they're tied to particular planes in this case. All right, so we can take those from the peaks. We will get DHKL values from Bragg's law, and we can take that interplanar spacing DHKL and find the lattice parameter A, which tells us about the structure of this material. So we can basically use the HKL values and the D spacings to obtain what structure we have and what the lattice parameter of that structure is. That's what X-ray diffraction can tell us. So if we're looking at non-cubic systems, we have different relationships between the interplanar spacing and HKL values and the lattice parameters, because we often have multiple, right? Hexagonal has A and C, tetragonal has A and C as well, and we often have A, B, and C. So there's different relationships that we have for different systems. So that's something to keep in mind if you're dealing with non-cubic systems. All right, so here's just a quick thing about quote-unquote missing peaks. So if we make the comparison between a primitive structure like this, and we want to look at the diffraction of the sort of 001 type planes, so the yellow ones, right? If we look at, so we would see those diffract in a simple cubic. But if we have body-centered, for example, where an extra atom is in the center here, we have an extra sort of plane that interferes with those others because it's halfway in the middle. And so this ends up canceling out the diffraction of those 001 planes. And so for BCC, we don't in fact see the 001. And so that's important because if we are looking at BCC, we don't expect to see diffraction from 001 because of this interference that we have. And so if you kind of go through all of those missing peaks, so to speak, or what we call the reflection rules, you see that all of the structures have some type of restrictions except for cubic. And so those restrictions, or what reflections are going to be present, tell us about what kind of structure. So BCC has a particular ordering of peaks that we see from different HKL values, and it's on the rule here is H plus K plus L are always even. FCC is going to have a different rule where all of the values for HK and L are either all odd or all even. And then diamond cubic, which isn't listed here, has additional rules as well, whereas simple cubic has all reflections possible. So it may seem like a bad thing, but this actually helps us differentiate the different structures based on what peaks are present.